Hi, welcome to another Andy's Workshop project video. This time I've gone and built a frequency counter, and in this video I'll show you a few things about it. Basically I'll walk through the build, how I put it together. We'll do some test measurements on some crystal oscillators to see how accurate they are, and I'll show you how I calibrate this board. This video has an accompanying article on my website, of course, and I do encourage you to click on the link that's on display now and read the write-up, see how I did it, and basically enjoy the rest of the video. Firstly, let's have a look at the board itself. This is a blank copy. I got these made by PCBWay, who I've never actually used before. Normally I would use Electro for my designs. But this particular board is a 4-layer board because I needed to use control impedance traces around the RF inputs for the sample and the external reference clock. I also didn't particularly fancy routing all the decoupling capacitors for the FPGA that's on here on a 2-layer board. I have done that before and it's a major pain. Well, if you go to 4 layers, it's much easier because you can run the power traces on layer 3. And of course you have the constant unbroken ground plane on layer 2, so you can really make the design a lot more compact and have far fewer traces running around all over the place. So, and at the time PCBWay were offering a very good price on 4-layer boards. I think this cost me about $40 for manufacturing, and you get 10 copies, and this is a 10 by 10 board. So that $40 plus delivery wasn't too bad at all. So I went for it, and I was quite pleased with the quality that they came up with. I didn't know what to expect, and I think generally speaking, I think these 4-layer boards are a notch up in quality from the 2-layer boards that you often use from those prototypes PCB houses. Now, one area of the boards I was particularly pleased to see where they did well is around the footprint for the QFN here. QFNs are a difficult part to solder, let's make no mistake about that, and you need all the help you can get. And if you look, you can probably see in high def, if you're watching in high def there, better than I can on the little video screen monitor that I'm looking at. But they've managed to get the solder mask in between the pads there. And that's really important for avoiding bridges between them during the reflow process. So I was really pleased to see consistent tiny little solder mask slivers all the way around there. That's going to be really helpful when I build this thing, because QFNs, let's face it, they're a pain in the neck. And I don't know whether it comes through particularly well on the video here, but I noticed that the solder mask registration, basically the accuracy of the positioning of the mask around the pads, is also particularly good on this PCBWay board. I noticed that it's very accurate, and also the drill positioning through the vias is also pretty much dead center in each one of these vias. So I am impressed with the manufacturing quality that these 4-layer boards come out with. I think that the agencies like PCBWay and SEED and ITEED and whatnot all send these 4-layer boards to a different house. So I think you're getting the benefit of a higher quality process from a different board house. So I am pleased with the way this has come out. Now, and in case you're wondering, the colours that I've chosen, it's the yellow solder mask that I chose because I thought it would look good on top of the. If I strip away don't put a ground fill on the top, basically strip away all the copper, then the yellow traces look really nice. They look kind of very electric. Before I move on to the populated board, let's just have a quick look at this feature here. It's something you can include on your own 4-layer boards, and it basically protects you against manufacturing errors, or it doesn't protect you against them, it allows you to detect them when they happen, because it is quite possible for the manufacturer to get the layer stack wrong. They could potentially put layer 3 above layer 2, basically swap around the inner layers, and you wouldn't know because the design would still work, all the continuity would be correct, but your controlled impedance traces would be all wrong because they'd no longer be referenced to the ground plane. So what this little window in the copper allows you to do is see the layer stack by stripping away the copper on all of the layers and then just putting numbers into the window space. The numbers are actually in the copper itself, 1, 2, 3 and 4. So as you look down at it, you should see numbers 1, 2, 3 and 4 fading away in different levels of intensities, and that will allow you to check that the manufacturer's got the stack right numbers. Because this is at a glance easy checks these got it right, and they have, because this is the bottom layer, number 4 obviously the bottom, and then I can only see through to number 3 just, and on the top, as we've just seen, we've got 1 and 2. So I know now that the manufacturer has got the layer stack correct on the inside of the board, which is obviously the part I can't see. And I know that my control impedance traces around the BNC inputs are going to be all 50 ohm as I calculated. So here's a populated board. I built this up using my reflow oven project, the Android reflow oven project that you can see on my website. And obviously, if you haven't read that, I do encourage you to go and have a look and see the videos that accompany it. But let's go through a quick walkthrough of the basic building blocks of this board. I won't go into the detail at this point, just the blocks. So this is the sample input. You connect your unknown frequency to here. The frequency comes out, goes through some analog conditioning and isolation stages here before going into an LTC6957 buffer. Now that's a very high quality frequency buffer. It's produced by Linear Tech, and the sample then, after it comes out of this, it's now a square wave, and it goes all the way into the FPGA. That way it forms one of the count inputs. Now the other important block before we leave the FPGA is this here. This is a Connor Winfield M100 temperature compensated oscillator. It's got a temperature stability of 100 parts per billion. It's a particularly good one. Now that generates a 10 megahertz reference frequency. The reference frequency comes out down this line here into this AD9553 PLL. Now this PLL is used to multiply up the 10 megahertz reference frequency to 200 megahertz, where it goes through a very short transmission line basically into the FPGA. So now the FPGA has got the 200 megahertz reference frequency, and it's got the unknown sample frequency. Now the logic that I built into the FPGA is then used to do the counting, basically the algorithm of the frequency counter that you can see if you read on my web page. And then that goes on continually regardless of what's happening. So the MCU here, this is an STM32F072, is used to coordinate all of the activities of the rest of the board. So what it does is ask the FPGA to start counting, and it gives it a gate counter, which is the time that it needs to do the actual counting. And then when the FPGA is finished doing the counting, it will raise a flag, basically a pin goes high, and the MCU then comes back to the FPGA and asks for the 2 total counts over the gate period. Those two counts come back. It's like an SPI interface between the two. It's kind of similar, but actually very similar to SPI. So the 2 counts come back to the MCU, and the MCU then makes those counts available to the display. What display, I hear you say? There isn't a display on here. No, you're quite right, there isn't. Rather than putting an LCD display on the board and complicating matters, and you can see there's not really any space for a display anyway. It would have to be on some kind of daughter board. So what I did was make the whole thing controllable over Bluetooth. That's an HC06 little Bluetooth board that you can get on eBay, and I've tacked it down below there with a double-sided pad. So basically the whole thing is orchestrated by an Android device. The Android device is used to set all the options, and it's used to come back and ask for the measured frequencies. You can use any Android device, basically just like this, for example, is in my phone, this or a tablet. They all work fine. So let's look at these parts of the board again in a bit more high resolution. So you can see the 2 inputs here. Basically this input is for samples, and this is for when I'm not using the onboard crystal oscillator, the Connor Winfield M100. If I want to use an external frequency standard, then I apply it here. The analog input stages here, I take no credit for the design of this. This came from a Linear Technology application note, which it basically tells you how best to use the LTC6957 in this kind of application. So I used that circuit exactly, and it's duplicated across to the external reference input here. They're basically 2 copies of each other. So the one on the right here, as we said, the sample input just goes out of the LTC6957 and into the FPGA. The external reference input one comes out of the 6957 and into the AD9553. The AD9553 PLL is a dual input PLL. You can see the 2 inputs going in there, 2 traces. One's from the external reference and one's from the onboard reference. and the selection between them is done via the MCU. There's a pin that allows you to select between the two inputs, and the output goes into the FPGA. The FPGA there is my Xilinx Spartan 3. I actually literally have 400 and something of these FPGAs, which I got for a good price. I have no idea what I'm going to do with 400 FPGAs, but I can at least start by using some of them on projects like this. So that device is in a VQ100 package. It's quite easy to solder, and any of these quad flat packs are easy to reflow. Moving over here, we have the STM32F072. I used the 072 primarily because it's got 128K of RAM flash. It's got 16K of RAM, if I remember correctly. But I needed more than normal flash space here, because the way I program the FPGA is that I compile the entire bit stream for the FPGA into flash, and then I use the MCU to program what's called slave serial mode by Xilinx. And I take the data straight from flash, and I program the FPGA on startup using it, and it means I don't have to have any external PROM components or anything like that to program the FPGA. I can do it in the MCU, and that just saves me parts and cost and all the rest of it, because the 072 is pretty cheap anyway. It's about £2 or something in units of 1 from Farnell. One nice side effect of picking an 072 is that it has built-in USB support, so if I ever decide to do something like data logging or anything like that over USB, then I could do so. Presently I'm just using USB for power, but I have wired up the data lines, and you can see there's the ST Micro USB LC6 ESD protection device on the data lines there, just to make sure that I don't inadvertently blow the thing up if I'm carrying static and I accidentally touch one of these things. Down here we've got the power supplies for the FPGA. FPGAs are a pain in the neck when it comes to power. They need, this particular one needs 1.2, 2.5, and it needs your VCCO, as they call it, which is your operating voltage, and I'm operating it at 3.3. So I've got 3 power supplies, one for 1.2, one for 2.5, and one for 3.3. As you can see, lots of grounding and vias here, going through multiple vias to the ground plane and to the power planes. Now, in my previous FPGA based design, the graphics accelerator, if you haven't seen the graphics accelerator, please visit the website or have a look through YouTube videos here. It's probably my most difficult project yet, and I'm quite pleased with it. But if you saw that project, one thing that I noticed was that the FPGA consumed a lot of power, more than I thought it would, and the AMS117 that I use, which is this IC here, was getting very hot. So I had to turn down the input voltage to the AMS117 as far as I could, just so that there was less heat being burned up inside the thing. This time I decided I'd take no chances and have a huge PCB-based heatsink on there, and this is mirrored on the bottom as well. I chose this size specifically to fit the little cheap sort of RAM heatsinks, aluminium heatsinks that you can buy on eBay, so that if this thing did get hot, even with all this area to wick away the heat, I'd be able to stick on a heatsink in that little square there. It didn't actually get that hot. This doesn't get that hot. This design doesn't consume nearly as much power as the graphics accelerator does. But hey, it's better to be safe than sorry. I didn't fancy respinning a board or having these AMS117 burning up. Okay, last thing to point out is the programming header. That's an SWD header, and it's compatible directly with the ST-Link V2 programming device, so I can just stick a cable on there and program it. 20 pins, too big, but hey, that's how big the cable is for the ST-Link, and it's just convenient, and I've got the space. One last thing to note, since we were talking about power in the last segment, is that these are the local power supplies here for the sensitive components. These are TI LP5907 ultra low noise, low dropout regulators, and they're used to supply power to the analog components, the LTC5907. There's one there supplying that, and there's one there supplying that, and there's another one up there supplying the PLL and the oscillator. Having little local regulators like that cuts down on noise, as does having via arrays like this that go straight down to the ground plane down below. Right, let's do some frequency counting. In this setup here, I'm using my my 7-inch Irulu Chinese cheap sort of plasticky Android tablet that I got on eBay or Amazon. Can't remember which one. I think it was Amazon actually. It's the X1 Pro, X1S or something like that. I forget the name. But I bought it because it has a nice IPS display, which it's nice and bright. You can watch from any angle. And it's got Bluetooth, obviously. It probably has the world's most temperamental Bluetooth implementation. I frequently have to turn Bluetooth off on this tablet and then back on again for it to pair with anything. You know, contrast that with a high quality implementation in something like a Samsung phone or an HTC phone where the connection is just instantaneous. But you know, that's the price you pay for going cheap, I guess. But 7 inches is a great size for a tablet, in my opinion. It's just right for a little display like this. So what have we got? Connected to the frequency counter, we have got a little Arduino board here, also from eBay, and I programmed it to output the clock, the MCO output to digital 8. So basically, that 16 megahertz crystal that you can probably just see on the board, it goes into creates the clock for the Arduino, which is then output directly on MCO. So we'll see how accurate that clock is. The frequency counter itself is already running. You can see that down here with all the lights are on. The green light is particularly important because that means that the PLL is locked. I had all sorts of problems locking the PLL when I first built this board, and it was basically a software problem. You can read about it on my website. But you know, you've really got to work hard at getting the right values for the you know, the registers inside this. And Analog Devices on their forums were exceptionally helpful in getting this resolved, and I really appreciate that. And I would certainly advise people to buy Analog Devices parts, because you know, the support is so good and it is there. So many manufacturers will just ignore you unless you buy a million. Analog Devices, not so. Good people recommend their parts. So let's launch the application. It is Nanocounter. I've christened this device Nanocounter. Couldn't find anybody else's frequency counter called that, so I think I'm safe. Let's launch the app. There's a Bluetooth connection, and we are off. And we can immediately see the frequency of the measured frequency is very close to 16 megahertz. I'm just going to have a look. I've got a gate time of 5 seconds here, that's fine. I was going to reduce that so you could see it ticking faster. In fact, I will. We'll go up to the settings menu up here in the Android app, and the Nanocounter group, and we can see the various things you can customize. You can change the Bluetooth ID if it doesn't happen to be HC06. Some of them aren't. Gate seconds 5 there. The reference frequency source is the onboard Connor Winfield. Haven't got an external frequency standard plugged into this. And these these reference filter and sample filter things refer to a feature of the LTC 6957. You can program in it's a bandpass filter basically, and because I'm not taking it, haven't got anything higher than 50 megahertz. I've just lowered it to 50 megahertz from the full range. Basically, you should be able to get a bit of a cleaner signal. Although I haven't noticed any difference in my tests. So I'll reduce the gate seconds to let's go down to 1 second. Say OK. That'll take effect immediately. What's happened there is that the new gate counter was transmitted over Bluetooth to the FPGA, where it now starts operating at 1 second, 1 second samples. And let's have a walk through how the display is set up here. Pride of place, as it should be, is the frequency count itself. There we have very close to 16 megahertz, and it's pretty stable. You can hardly see any change here. It's a decent. I would have thought that crystal was going to be the cheapest part that the Chinese could get their hands on, because it's the whole unit, the whole Arduino unit sells for about £2. I just don't know how they do it. I mean, they can't be using top drawer components, but it's not bad. It's pretty stable. So there's a count there, the number of samples received, minimum, maximum, average. Yeah, that's all so. Gate seconds, yes, that just tells me the gate counter, what the reference frequency source is. The filter, reference filter isn't applicable because it's on board. And my sample filter is set to 50 megahertz bandwidth. And I've got a little readout there of the MCU core temperature, which might be interesting to some people. I could measure it, so I did. The little scrolling thing here just shows the whether the current sample is up, down, or unchanged from the previous one. It's a quick view of the sort of short-term stability of the frequency. Down at the bottom here we've got a chart, a little Android chart of all the frequencies received, so you can see the performance over time. And we'll have a bit of fun in a minute just to see how these things change, how these crystals are stable with temperature or not, as the case may be. So up here in this little panel at the top right is the, it's basically, I set what the ideal frequency is. I can do that in my display settings here. So if I go to settings, display, I can say what the ideal frequency of the crystal is. In this case it's 16 megahertz. I can say that the tracking versus the ideal frequency is on the most recent sample. I can change that to be, you know, min, max, average, most recent, whatever. So what that actually means is, back here, now that I know what the ideal frequency is and I know what the sampled frequency is, I can figure out what the actual ppm rating is, the current ppm is for this crystal. And for this crystal, it's under, it's slow by minus 32 ppm, which is pretty good actually. For the cheapest possible thing I'm sure they could lay their hands on, just being 32 ppm off nominal isn't bad at all. And this number here, which says minus 116 milliseconds per hour, is the correction factor that I would have to apply to a clock based on a millisecond timer to make it accurate every hour. So basically I would have to subtract 116 milliseconds from the millisecond counter every hour to keep a clock based on this particular crystal to keep it accurate, as long as the temperature doesn't change, of course, because these things vary with temperature. And the reason I put that up there is because the whole point of me doing this in the first place was to try and build a project based on a cheapo Arduino like that would run for a long time and accurately timestamp the data it was acquiring. And it didn't take me long to realise that with a crystal that's off by a bit, then I wouldn't be able to do accurate timing at all. So I'd have to apply a calibration factor, and therefore I would need to know how well the crystal was performing, and this is why I built this project. And now this project is better than the one I was working on for the data acquisition. That's just the way things go. Right, let's have some fun looking at the temperature stability of these things, the crystals that is. Now I've got my multimeter here which has got a temperature reading attachment, and it's showing that ambient temperature in this room is about 24 degrees, which is, you know, it's about, I think that's a bit optimistic by a degree or so, but I'll take that. So firstly let's stick the temperature probe on the crystal here and see what happens. I think I know what's going to happen. I'm going to get a reading which should be ambient. Yeah, it's 24 degrees, but look at the frequency output in the counter, it's dropped. Just touching the metal can there with this metal probe has caused the output frequency to drop by 100 Hertz or so. I don't know, I expect that's a capacitance thing, but I'm not entirely sure as to what's going on there. I doubt it's temperature change, so it must be capacitance that's slowing the crystal down. So if I take that off, then it'll go up, there it goes, starts to rise, and then go stable again. So I've got a cup of tea here. I'm going to warm my hands up on it, and yeah, let's get my fingers warm, and then grasp the end of this thing, and we'll see how hot I can make it. Yeah, I can get it to about 32 degrees. So if I then warm my fingers up again, so I can get it right, and I'm going to touch the crystal and see what happens. Put my thumb on it. There we go again. Quite a big change. Now instead of being off, yeah, it's quite a big change. Instead of being off by 31 ppm and stable, it's all over the place as it warms up. Yeah, you can see the change there each time. Okay, so I'll take my finger off and let it settle back down again to its stable frequency. It actually wasn't too bad there. Quite impressed with the way it sort of held on. A few ppm off, just by temperature change of like 8 degrees or so. It isn't bad at all. Now let's take a look at the performance of an internal oscillator built into the MCU itself. Quite a few modern MCUs offer this facility, basically so you can have crystal-less operation. It cuts down on cost. And it does this by embedding a little oscillator on board the MCU itself, and you can use that to generate the core clock frequency and various others for use within the device. But they're a lot less accurate than an external crystal, as you can see here. For this demo, it's out with the Arduino and in with the STM32. This is an F051 development board, the discovery board. And I've programmed it to output the HSI, the internal oscillator, on PA8. And I've got that hooked up to the counter, and we can see what it's doing. I mean, you can see it's actually all over the place. If you remember previously, the external crystal on that little Arduino board was only 500 Hertz off its rated frequency, which is pretty good, 31 ppm. Compare that to the 8 megahertz internal oscillator here, and this, you can see it's unstable and it's all over the place. Now, for most applications, it's going to be close enough where timing doesn't matter, because if you do the maths, that's only 0.5% off 8 megahertz, so it's not a huge amount when you think about it. But as an absolute frequency number, it's up to 36, 37 kilohertz off the ideal frequency, which puts it at 4,500 ppm. Or to put it another way, I would have to correct that clock. I mean, if I could even correct it, because it's so unstable, I'd have to correct it by 16,000 milliseconds per hour. So what that's telling me is that if I were to base a real-time clock or a data logging thing off this off a device using this internal oscillator, it would gain 16 seconds every hour. That's pretty poor. It gives you an idea that if you do need accurate clocking in your designs, you shouldn't rely on the internal oscillator. Now, this oscillator can be calibrated. You can calibrate it in something like 34 or 35 kilohertz steps. I forget what exactly it is. So I could get fairly close to the the nominal frequency. But as you can see, it's unstable. It does kind of go all over the place. Look at the chart down here. Compared to the flat chart that you saw with the external crystal, the internal one is everywhere. Let's see if I can. I'll just put my finger on the MCU and see if I can make it change even more. Let's change the temperature. 36.4, 35.9, 35.8, 35.7, 35.6. So it's changing. It is definitely changing as I heat up the MCU with my finger there, and that's probably as hot as it's going to get. So if I take my finger off, it should start to go back up to wherever it was before. 35.8, 35.7. I don't think the temperature's changing much actually. 36, yeah, it is rising slowly, but it's so unstable it's difficult to see the overall trend without looking at the chart down here. So there you go. Now you know exactly how the internal oscillators on these devices perform. So if you need accurate clocking, for example, if you were to be doing USB, then you can't rely on this internal oscillator without having it continually corrected in software. Okay, calibration time. What I've done now is I've hooked up a frequency standard, a 10 megahertz GPS disciplined oscillator, to the sample input port. Now, if you haven't come across GPS disciplined oscillators before, they are exceptionally accurate frequency standards. Basically, they're as near as damn it to 10 megahertz plus loads of decimal places. So they can be used to calibrate your own crystals that may not be as accurate. I won't go into great depth about the GPSDO because I want to do some separate videos on the one that I've got where I'll tear it down and show you what's inside these things and how they work. But mine's now warmed up, it's connected, it's telling me it's locked to the GPS signal, and the ovenized oscillator inside the thing is ticking away at 10 megahertz exactly. So by connecting it to the sample port, what we're actually seeing on the display here is the performance of the reference oscillator on the PCB. We know that the GPSDO is exactly 10 megahertz. And now what we're seeing at the moment is that the reference oscillator on the board is off by 4 hertz. Because the way the frequency is calculated based on the counters means that you can use it either way around, the reference frequency versus sample frequency. It's the same kind of ratio you use to get the frequency output here. So now using this frequency standard connected to the sample input, I can calibrate this and say, well, all I need to do is add 4 hertz to make this thing bang on. It's actually 4 and a bit, so if I go to the settings menu, display, let's up the number of decimal places to 2 here, and let's go back you'll see that it's off by 4 and a bit hertz. If you look at the ideal frequency here, which I've set to be 10 megahertz, it's calculated that it's off by 400 parts per billion. If you look at Connor Winfield's datasheet for this particular oscillator, that is within range. If my ambient temperature in this room was 25 degrees C, it's not. It's about 21. Then I would expect that its value to come down a bit. The actual value that it's off by depends on lots of things. The capacitive load that's applied to the output will change the frequency slightly. I've added some capacitance on, you've seen the schematic, to try and bring this close to what I estimate would be ideal, but it's still going to be off by a few tens of parts per billion because of that mismatched capacitance. So still, we're talking parts per billion here. Remember, this is 0.4 ppm. This thing is really accurate. So to calibrate, what I do is I go to my calibration settings, which replaces the table that we see on the inside of the display here with the calibration settings. You can see that the last time that I calibrated this device was on the 20th of February, and I put in a value of 4.25 plus 4.25 to match it. It's easy to do. I just press auto there and it calculates the difference from 10 megahertz, and I enter the current ambient temperature, which in this case is about 21 degrees. And I can hit save. I'm not going to do it now because I don't need to calibrate it again today. But if I hit save, it transmits it over to the MCU. Now the MCU maintains the calibration history of up to 112 entries, because that's how much space I had in a page basically. It maintains that history inside a flash page, inside its flash memory. And it's read back on startup by this device, and I can show the history and it will always apply the most recent one. So if I close that and I go back here and I apply the last calibration, you can see that it's basically nearly on 10 megahertz. And since I always put my settings on 0, it's going to round up, frequency decimal places, back to 0, and we should have a good measurement of 10 megahertz. It's obviously it's now hiding the frequency decimal places there. So you can see that since the last time I calibrated this on the 20th of February, the temperature obviously in this room has changed maybe a degree or so, depending on what the weather's like outside and whether I've got the heating on or not. And you can see it's moved by about 25 parts per billion or so, and it's changing ever so slightly there as time passes, but it's well within spec, and we're talking about tens of parts per billion. So I'm very happy with the performance of that Connor Winfield oscillator. And of course, if I need to measure absolutely perfectly to the nth degree, then I can just take my GPSDO from the sample input and put it onto the external reference, and that will then override the Connor Winfield and take precedence. And I'll be able to do absolutely perfect measurements against the perfect 10 megahertz frequency standard. And just for fun, here it is on my phone. The HTC One M8's got a much higher resolution display than that cheapo tablet, and you get to see a bit more chart space on the bottom, but basically it works on any Android device. Well, I think I've shown you everything, which means that's all I have for you today. There's much more on my website. There's all the circuit diagrams, the PCB layouts, all the write-up there in detail. The software that behind this is all free. It's all available on GitHub. Links available at my website. This is entirely open source, so if you fancy building your own based on this model, then feel free to go for it. And I'm there to help you if you come across any problems. So catch you next time.